Yeah, so about Pearson Plus, do you think that's a good like tool to use for like studying each chapter and stuff? Because I noticed for each chapter there's like a worksheet that we can print out.
Yeah, I haven't looked at those accoutrements yet myself. This is sort of new to this new, not even to this new edition, but they even made a whole new website I think it
Right.
was last semester. So I haven't looked at those, but I suspect they're pretty good. And I've been a part of writing the solutions manual and the websites for this particular textbook and
Okay.
a couple other previous editions, and all those things that they put up were generally good. So I would say, yeah, that might be a really good spot. I would try it, say on the first and second chapter, and see if you do pretty well the first time you try to take my practice tests for test one. And if you do, then that's a good indicator that it's working. If you want to really test it, then try not doing it the next practice test and see if you know it better or worse. But yeah, I would suspect it's going to be pretty good that way. You also have the other resources, of course, my YouTube channel. You've got Khan Academy. You've got certain videos that they put within the links within the textbook itself. But yeah, all that stuff. But do let me know how it works for you. I'd be curious to hear student feedback on that.
Sounds good. Thank you.
Yeah. Sorry, I couldn't tell you more specifically whether it's good or not, but in the past, we've had things like there used to be a publication that they put, God, I can't remember the name of it, but I know that that particular manual was really nice and it was asking very specific conceptual questions. So it helped you better understand the concepts in addition to the equations that you're learning. So I think they were called lecture tutorials. That's what it was, lecture tutorials. And they just had a lot of questions like, does the acceleration of an object being negative imply that the object is slowing down? Stuff like that. Those are great conceptual questions that I just don't have time to address because I have to teach you the quote unquote more complicated stuff that's, solving equations, word problems, that kind of stuff. But yeah, those are really excellent tools in general. So if it's asking questions like that, that definitely is. I'll try to look at it over the weekend and give you some actual feedback based on what I know of it, but I'll check some of it out this weekend. All right, it's 5:30, so it's technically time to go ahead and start class. So, I always intend at the beginning of class to take questions, even though I do try to log in early in case people have questions beforehand, so we don't use class as much class time. But if I ever just jump into class, because I often do that, getting a little bit excited because I like my subject, I love teaching, and I like teaching and interacting with students. So occasionally I just get excited and jump into my lecture without actually remembering to ask you if you have questions. So if I ever do that, you go ahead and tell me, "Hey, Mr. Younger, I have a question," and you stop me. It's not rude. I'll completely understand. Additionally, I forgot to tell you guys last time. I do put these videos on my YouTube channel. So if you have a problem with that, for instance, if you have your name appearing on the internet as a problem, you should probably go ahead and change your name, your username within Zoom to something else. Maybe, like your first letter of your first name and then some abbreviation of your last name or something a little less obvious. Or you could put the last four digits of your student ID so that I could tell who that is. But the main thing is once you chat this, that never goes up on my YouTube channel, so you shouldn't be able to see that. So just let me know that name. That'll be fine. Additionally, if you can't be seen, do not only change that, but let me know so I can try to make extra sure that none of your names pop up because occasionally, for instance, when I switch to log in, letting you guys log in, your name pops up in the whole screen and stuff like that. So if I see that and I know you're a student that doesn't want that to be on the internet, then I'll do my best to edit it out. And if it gets, too problematic, then I just never will post the video. But I'll post it in a closed setting where you guys can access it and only you. But please let me know that. I know, sometimes there might be something going on. Maybe you're in witness protection program from the mob or something. I don't know. But the main thing is I don't want to harm anybody. So if any of you have any concerns like that, please let me know. I'll keep it on the down low, as much as I can, which should be a lot. But the only thing that would mess that up would me be being doing something stupid by accident. So I apologize in advance if I do that, but I'll do my best not to. I did go ahead and tell everybody to go ahead and chat me your first and last name, so feel free to do that. And try to help me remember to tell everybody else to do that because people are still going to straggle in after I've made that announcement now. But I'm going to go ahead and get started. After I ask one more time, does anybody have any questions? Need any help on homework? Have any problems they tried to work in homework and didn't understand? Any of that kind of stuff? I want to also, since I've opened that floor, y'all just speak up if you have a question. But I also want to remind you, you do have homework due Sunday at 11:59 p.m. and there's no excuse for it being late. So make sure you get that done. If you don't, it's going to have points taken off. Okay. So no questions, it looks like. All right. Well, let's go ahead and get started. So last time I broke in with starting a little bit of information about the syllabus, more information about the SI system, a little bit about the scientific method. I didn't talk very much at all about that with you guys in this internet class, but there's plenty of that on my YouTube channel and in the links that I gave you in week one module, which I will call module one, and week two module I'll call module two, even though it doesn't say anywhere module one or module two. So just remember when I say module one, I mean week one. And when I say module 18, I mean week 18. Okay. So it's the module for that particular week. That being said, we got through the prefixes. Remember T dot dot G dot dot M dot K, hecto, deca, base, deci, centi, milli, dot micro, dot nano, dot pico are the SI prefixes, and each of those prefixes, as well as the dots, represent a power of 10. So if you go from the base to the left, you first run into deca, which is 10 to the first power, then hecto, which is 10 to the second power, which is 100, and then kilo, which is 10 to the third power, 1,000, then dot capital M, that's mega 10 to the 6, capital G is 10 to the 9, capital T is 10 to the 12. On the other end, it's 10 to the negative 1 for deci, 10 to the negative 2 for milli, 10 to the negative 3 for for milli. I said that backwards. 10 to the negative 1 are 1 over 10 for deci, 10 to the negative 2 are 1 over 100 for centi, 10 to the negative 3 for milli, which is 1 over 1,000, and then micros 10 to the negative 6, nanos 10 to the negative ninth, and picos 10 to the negative 12th. Uh, those I expressed last time not only are ways that you can learn the prefixes, but also that's a way to make what I called an equivalent statement. So, for instance, the fact that tera is 10 to the 12th means that 1 terameter is 10 to the 12th meters. Therefore, you have now an equivalent statement. 1 terameter equals 1 times 10 to the 12th meters. Similarly, the fact that, for instance, nano is 10 to the negative ninth, that means that 10 to the negative ninth meters is equal to 1 nanometer. So notice there's a little difference in the way I said that. That's important, but that's the way you make up an equivalent statement. And when you have an equivalent statement, that means you can take the two sides of the equals and put one in the numerator and the other one in the denominator, and that makes a fraction that's equal to one. You could also flip it over, and that also makes a fraction that's equal to one. And when you multiply a number by one, you don't change its value. So that's why we do that. there's certain types of units that only are converted via multiplication, and units that work that way are designed or can be used in such a way that you multiply by one in such a way that the unit you have disappears and the unit you want appears. And when you do that, that multiplication by one gives you the right unit conversion. If you multiply by one in such a way that the unit that you want doesn't appear and the unit that you don't want doesn't disappear, then you will not get the right answer. Your book tells you that, but I just want to reiterate it. So keep that in mind. That being said, there's other types of units as well. For instance, the conversion of Celsius to Kelvin or the conversion of Fahrenheit to Rankine. Those are ones where they're additive conversions. So, for instance, if you have 0 degrees Celsius, in order to make that Kelvin, you have to add to the 0 degrees Celsius 273.15 Kelvin. So, 0 degrees Celsius is the equivalent of 273.15 Kelvin. That's not going to work by multiplying by one. Fahrenheit to Celsius is a linear relationship, so that's another one that you can't just multiply. Has anybody ever heard of the unit of the decibel? Decibell, or actually, I think it's one L. Anyways,
Yes.
if you have heard of that, so
Uh,
yeah, you probably heard of that in the realm of sound. But if you're into electronics or you work for a cable company or Dish Network or some other satellite television company, you might know of it as well. It's a more generic term than you think, but it is deci. Notice that sounds like one of the prefixes from SI. That's because it is. It's 1/10 of a bell. A decibel is 1/10 of a bell, and a bell is defined to be basically some number times the logarithm of the intensity. So in that case, to actually convert decibels, you have to basically realize that a decibel is made of a logarithm. So the opposite of a logarithm is an exponential, and so on and so forth. So that's another type of unit that doesn't. But that decibel can also be used to talk about how much a signal attenuates, like from the telephone pole or some kind of pole out there, where the cable company, for instance, picks up the line for cable, and then when it gets here into my house, that same coaxial line will have a less intense signal, and they will measure the intensity there in decibels. So that's another instance in which decibels are used. So I've just told you three different ways that units can be converted that don't require multiplication. But to be honest with you, there's very rare cases, other than those ones I mentioned to you, that use something other than multiplication. So this gets you the vast majority of unit conversions. I'll also tell you that uh, unit conversions have gotten me literally promotions in the history of my life. Like one case, it was me working as a lifeguard, and then all of a sudden I became the pool operator, and literally went from 7.50 an hour to $15 an hour, just because I took the time to read the manual that came with the test kit. And I realized that everything they did in the manual was just unit conversions. And I was talking to the pool manager who was doing like three jobs at the time. He was the landscape manager, as well as the trolley manager, as well as the pool manager. And when he realized I knew what I was talking about, he asked me if I wanted to be the pool operator. I said, "Well, I don't have that certification." He said, "We'll pay you to go there, and we'll give you a raise." So that's been a wonderful thing. It also happened when I was working as an engineer, when basically an engineer hadn't done the calculations for a wastewater treatment plant in several years. By the time they started building it, the health department came in and asked him a bunch of very specific questions with calculations, and he was like, it's going to take me a long time to figure that out." But he looked at my resume and said, "You seem to know a little bit about math and physics, so here's a copy of." It's a book that's more or less like the Bible of wastewater treatment. It's called Metcalf and Eddy. He said, "Here, take this book." And I kid you not, it's that thick. He said, "And see if you can make some sense out of this email." And sure enough, I was able to look at it and I realized that all of wastewater treatment is essentially a linear relationship and therefore it's like unit conversions. And I was immediately able to diagnose what had happened and actually corrected them and saved the company a lot of money, really. So they immediately pulled me out of the field. I was working as a surveyor just because I had just been laid off after 9/11. I was just looking for some work to be able to do other than, working at Home Depot or whatever, which I was working at. So they moved me from in the field as a surveyor to a CAD technician as well as a engineering technician and started working that way. Again, with an increase in salary. So this unit conversion stuff is super powerful. Uh, I'll ask one more time because several people have now come in since I said it before. But does anybody have any questions before we get started on the rest of the material? Okay. I already said this before, but I'll say it again. Now's a good time for you to chat me your first and last name that I'll use for roles. So if you haven't done that already, go ahead. I'm going to go ahead and share my screen with you guys. So here I go. Okay, so this time I've taken the time, and I don't always have the time to do this. That's why I don't do it. Usually, what I do is I go through the book and real time and pull up an example. And I'm expecting you to have a copy, quote unquote, a copy of the book available to you, meaning specifically you should have your electronic copy of your book open so that I can say, hey, I'm going to work example 1.5 and I'll read it to you. If you need more than it read to you, then you can read it yourself or copy it down, but I don't take the time to write it. In this case, today, I actually had some time, so I went ahead and reworded some of the examples in an attempt to try to avoid copyright violation. Obviously, I may or may not have succeeded at that, but we'll find out. The main thing is I did do this, so it'll help us a little bit. So we're going on from where we did. Remember last time I showed you how to convert units. Specifically, I handled miles per hour. We found out that 60 miles per hour was like 26.8 meters per second. And in fact, your book does a similar example, but it used 55 miles per hour and they converted it to meters per second as well as to kilometers per hour. And the result there was 55 miles per hour is 25 meters per second, and it's also 88 kilometers per hour. So that might be a worthwhile thing to know and to keep in your head just so you can make quick estimates. I also did a unit conversion for the density of water, and there's an extra credit problem that you can work for that as well. There's also a extra credit problem associated with the fundamental mass unit. In other words, we have a standard mass that's stored in Paris, and it's a little cylinder of radius R and height H, and it's made of platinum. I think platinum iridium, specifically because that substance doesn't corrode very well. And because corrosion is the biggest thing that could actually cause it to change mass, what they tried to do is make this object uh, a geometry that minimized the surface area. So another extra credit you can do is do the calculation of minimizing the surface area and then do another operation to confirm that it's minimizing, not maximizing or finding the point of inflection. So those are some questions you can do as extra credit as well. Feel free to ask me about them if you need. I did a pretty lengthy discussion of exactly what you're doing in each of them. But either way, that showed us the last time when we did the unit conversions of kilograms per cubic meter to grams per cubic centimeter. That showed you how to deal with units that are raised to a power. So I'm essentially done with converting units, and I'm going on to the next section, which is where they're talking about estimating, quick calculations, what they call back of the envelope calculations. I will tell you that Larry Weinstein is a professor at ODU, the physics department. He's near retirement age, so I suspect he's going to be retiring in the near future if he hasn't already. I haven't spoke to him in about 2 years or so. But he wrote a really good book on this. It's called Guesstimation 2.0. Actually, I think his first one was just plain Guesstimation, and then his new edition was Guesstimation 2.0. But it tells you a lot of stuff about this. And I just tell you that because some of the fundamental rules that you're supposed to be able to do here is as a physics student, we expect you to understand the SI system. So what do I mean by that? I mean, like, you should be able to tell me whether the human body temperature is closer to 10 Celsius, 20 Celsius, 30 Celsius, 40 Celsius, or what. You should be able to tell me roughly how big is a centimeter, how big is a millimeter, how big is a meter. So, in other words, you need to be able to look at things and estimate how big they are in the SI system of units. So, in light of that, I will tell you that me personally have discovered that my pinky nail, its width is about 1 centimeter. My fingernail, specifically my thumbnail, is about half a millimeter thick. And I've seen a lot of elderly people in my life, and it turns out their toenails are on the order of a whole millimeter thick. And I've seen some that look like they might be 2 millimeters thick due to various fungi and old age and stuff like that. But that's another thing to keep in mind. The height of a doorknob is about a meter. The width of a staple is also about a centimeter, but the thickness of a staple is about a millimeter. Those are the kind of things you should be able to do. And in order to do that, some of the lessons that I learned from Larry Weinstein was one thing you can do if you look at something and say, I have no idea how big that is. Well, you can talk about powers of 10. So if I ask you how big is or how tall is a stop sign, you might not know exactly how tall it is. You probably don't know that it's very close to 3 meters or something like that. Or in many cases, it's actually closer to 2.5 meters. But what you can do is you say, well, I know it's bigger than a meter. And then I multiply a meter by 10 and I get 10 meters. And I say, okay, well, I know it's smaller than 10 meters. And since I know it's bigger than 1 meter and bigger than 10 meters, I take the geometric mean of those two figures. 1 meter times 10 meter is, of course, 10 square meters. And now I take the square root of that, and that's the geometric mean. The square root of 10, Larry will tell you, is approximately pi. But he'll also tell you that pi is approximately 3. So we're going to say that the height of a stop sign is approximately 3 meters. That's the way you do it. You just choose a number that it's bigger than, as close to it as possible, and then choose a number that it's smaller than, again, as close to it as possible, and multiply those two, take the square root, that's the geometric mean, and then round it to one decimal place. So that's a good thing to know how to do. And the estimate of the square root of 10 being about pi is pretty nice, easy to remember. So keep that in mind. So let's jump to this particular one. It says estimate the amount of water in a lake by assuming the lake is circular and about 1 kilometer across and has an average depth of 10 meters. Now that's a little bit more difficult. In order for you to come up with the average depth being about 10 meters and the height or the distance across it being about 1 kilometer, and it being circular, that takes a lot of stuff. Now, you might just happen to be dealing with a lake that does look kind of circular, in which case you're lucky. Uh, but you can also use Google Earth, and that can actually allow you to get a rough estimate of how big the diameter of a lake is. So that works. If you happen to be a scuba diver, maybe you dove this lake and you know it doesn't get any deeper than maybe 35, 40 feet every now and then. So that might be a worthwhile thing to say it's 10 meters, which is about 33, 35 feet, something like that. So with that in mind, let me show you how you go about estimating it. So solution, this is something else that physics assumes, and basically every author of every physics textbook assumes, in some sense, that you guys are the perfect student that went through the perfect high schools and learned everything you were supposed to in all of the classes you took. And not only that, you took all the classes that you, quote unquote, were supposed to take. I am a very, very different type of student. I was a horrible student all through grade school. I think I graduated third from last in a class of 60, and that was after a mulligan after, 3 years of high school, I got a mulligan and still graduated third from last in a class of 60. I didn't straighten up until my senior year, and only then did I get even remotely interested in going for physics and engineering. But anyways, because of that, I am like you. I haven't necessarily had all these criteria, but what I mean by that is, for instance, the typical textbook author for physics assumes that you had algebra 1, algebra 2, trigonometry, and geometry, and that not only did you have them, but you mastered everything that you learned in those, as well as your arithmetic facts. And you also have a rough estimate in your mind of, how big the Earth is, how tall Mount Everest is, how deep the Marianas Trench is, the fact that the surface of the Earth is about two-thirds water, so on and so forth. Just a lot of things they assume. So you got to be prepared for that, and this is a case in point. Uh, in this case, we're assuming that the water is going to be basically in the shape of a cylinder, and this diameter is 1 kilometer, and the depth of this cylinder is D, which is about 10 meters. Okay. So, my knowledge of geometry tells me that the volume of this lake would be pi times r squared times d. So, that again is that perfect understanding of geometry and complete mastery of geometry, which, by the way, I never even got far enough in school to take geometry. My senior year, I was doing so wonderfully that my guidance counselor called me in 2 weeks into my what I thought was my senior year to tell me that there was no way in heck I was graduating because I was short 3 math credits. So I ended up having to take what was called Algebra 1A, which was basically illegal now in North Carolina, but they would take Algebra 1 and spread it out over 2 years. So I took that. I took beginning math, which was really, really low level math. Literally, a kid in front of me had his name written in his underwear with magic marker. That's how bright the poor student was in front of me. And then I had business math. So those are the three math classes I had to take. Just to give you again a feel for, hey, that's okay that you haven't had geometry if you haven't. Uh, I'm going to teach you these things as we go. So the volume of a cylinder is power squared times the height. And now I'm going to go about doing this estimate. And it says estimate the amount of water. They didn't explicitly tell us what they mean by the amount of water. So I'm going to do both. I'm going to calculate the volume of the water and the mass of the water. So let's go about calculating it. So the volume is pi r squared times d. Uh, the pi I'm going to say is approximately 3 because again, when you're estimating, you really only need one sig fig. So pi being 3.14, I'm just going to call 3. R is actually half of the diameter. And the diameter is 1 kilometer or 1,000 meters. So I'm going to say the radius is 500 meters. And that's got to be squared. And then I'm going to say the depth is 10 meters. So if I square the 500, what I get is 5 squared is 25 and 100 squared is 10,000. 25 times 10,000 is 250,000. If I multiply that by 3, I get 750,000. If I multiply that by 10, I get 7,500,000. So I'm going to say this is roughly 8 times 10 to the sixth cubic meters. See how I did that? I didn't have to use my calculator or anything. I just did a calculation. I did, for a brief stint there, carry 2 sig figs because I multiplied 3 times 25 and got 75. But it came up to 7.5 million, which I called 8 million roughly. Okay. Now, 8 is really close to 10. It's way bigger than 5, right? So, in fact, I would say it's probably better to say that the volume of this pond is uh, 10 million cubic meters. So the volume is 10 million cubic meters. That's one answer. But I also recall this is something else that we sort of expect you to know, which is why I did that example last time. The density of water is
Wait,
1,000. Go ahead.
how did you go from 8 times 10 to the sixth to just 10 to the seventh?
8 is closer to 10 than it is to 1.
Okay,
So does that make sense now?
so we're just rounding up.
Yep. Yep. I,
Okay,
I just decided to round up. If it was like 6 or 7, I probably wouldn't, but 8 or 9, I would.
okay.
Okay. Now, knowing that we have 10 million kilograms, or excuse me, cubic meters of water tells me that the mass of the water would be equal to 10 to the 7 cubic meters times 10 to the third kilograms per cubic meter. And of course, that gives me 10 to the 10th kilograms. So 10 to the 10th kilograms is in fact 10 billion kilograms. Okay, so that's my two answers. I would say that pond has on the order of 10 million cubic meters of water, and it has on the order of 10 billion kilograms of water. And remember, a kilogram is about 2.2 pounds, so we're looking at, tens of thousands of tons of water. Anybody have any questions on that? All right, so that's how that one's done. Let's look at this next one. And feel free, like I said, to ask me questions as we go. This one says estimate the thickness of a piece of paper by looking at, in this case, I said a Latin and English dictionary. So I just happened to grab one of the books that's on my desk. Here it is. And you guys can see this. I'm a normal sized human. My head's not like only 8 centimeters tall or anything. So you can assume this sort of stacks up to you about the same way it stacks up to me. Anybody want to guess how thick that is? Because what I'm going to do is I'm going to use the thickness of all these pages and the number of pages to estimate the thickness of these pages. Anybody tell me in SI units how thick this book is? And we're really trying to ignore the cover and just go for the pages itself. So technically,
Uh, I'm gonna say 4 centimeters.
very good. That's not bad at all. In fact, I said 4 centimeters myself, and I wanted to check it. I thought it was a little less than 4 centimeters, and it turned out to be just a little under 3 centimeters. So either one would certainly be acceptable because we're looking for an order of magnitude, i.e., by a power of 10 estimate. So we're going to say the thickness. Ooh, of, and I've already checked the page number of 675 pages is about uh, 4 centimeters. Really, it'd be better to say 3 since I actually measured it, but since you guesstimated that, that's perfectly fine. We're going to go with it. So it's roughly 4 centimeters. Now, the pages, as I said, it has 675 pages. But how many pieces of paper is that? Anybody?
I want.
670.
Oh,
Mm-hmm.
Sorry.
Go ahead. Who? There was Colin was one person. I think I heard a female voice in there as well. Maybe. Who was that?
that was me, sir.
Oh, is it Jaden?
Yes, sir.
Gotcha. How many pages do you think that, or how many sheets do you think that is? You can tell me a fraction if you don't know don't want to do the math. That's fine.
I was gonna say one over. I think I said 121,
Oh, gotcha. I see.
somewhere
Okay.
in there.
Yeah, so each page has two numbers on, or each sheet has two numbers on it, like 670 and 671. So basically, what I'm trying to get at is if you say the number of pages in a book is 675, you'd want to roughly divide that by two because the number of sheets is twice as small. Does that make sense?
Makes sense.
Okay. So this is what we're going to do.
Are
Go ahead. Go ahead.
are we accounting for the cover pages that generally don't have numbers on them, like the front and back
Yeah,
cover?
I actually the my book happened to go up to like 643, and I counted the pages before it, and
Okay.
came up with 675. But yeah, that's exactly the kind of things you're supposed to think of. And also, you got to remember if you're talking about 675 pages. And 10 of those isn't that critical of a difference, but it's very good to think about it. And you certainly wouldn't want to start with 10, the number being off by minus 10 from the get go. So the fact that you're thinking of it's exactly what I want you guys to do is yeah, you always want to think about the details enough. And yeah, when I measured it without the front cover and the back cover. Okay. So now we're going to take that and get an estimate. The thickness of a page, or the thickness of a sheet, is the thickness of 333 sheets divided by 333, like that. So I'm going to say delta T equals the thickness is approximately 4 centimeters divided by 333. And you could say centimeters per sheet if you wanted, divided by sheets. And doing that kind of stuff, calling it 4 centimeters, 4 centimeters per 333 sheets. So I really shouldn't have done it that way. But sometimes adding things like sheets in the units is helpful. Sometimes it messes you up. Like in this case, it actually messed me up because I thought about the wrong thing. But either way, I'm going to say 4 centimeters over 333. And when I put that in my calculator, I'd say, ooh, oh crap, my calculator's all of a sudden telling me my battery's low. So 4 divided by 333 gives me 0.012 centimeters per sheet. So in terms of millimeters, we'd say about 0.1 millimeters is the thickness. And it turns out that's about the same answer that the book got when it did it with a different book and a different number of pages. So, anybody have any questions on that? That's just one way. There's a bunch of other ways. I want to tell you also that some of the types of questions that can come into play, you're going to see a couple more in a second, but some of them are like one time my physics instructor for the same class said, "How many houseflies could you fit in this classroom?" So literally in the classroom that we were talking, that we were sitting in, we were supposed to estimate the width of the classroom, the depth of the classroom, the height of the ceiling, and then estimate the size of an actual housefly. Make an assumption about the shape of the housefly so we can get an idea of the volume of the housefly, and then divide the volume of the room by the volume of the housefly to get the number of houseflies you could put in there. That's a very typical type of example. If you watch the Oppenheimer movie, or if you read the book by Kay Bird, American Prometheus, or any of these other books, you probably learned about Enrico Fermi watching the Trinity test. And when he's watching the Trinity test, he drops some bits of grass and dirt as the pressure wave comes to him. And immediately upon doing that, he estimates the yield of the bomb. Now, once that test is done, physicists go back and do a bunch of calculations using a bunch of equipment, and it takes on the order of hours to get an estimate of what that is. And he had the answer to one sig fig within seconds of it. And you might say, well, wow, how did he do that? Well, Larry explained that to me. He was the first one that explained it to me. I tried to figure it out myself and had an idea, but it wasn't the same idea he had. But it turned out that works really well. So if you read Larry Weinstein's book, you could actually learn that a little bit. But it's just one of the kind of things you should be able to do. Another one is how many pennies can you fit in a shoebox? Or I've seen a bunch of people on TikTok doing stuff like this, and it really aggravated me. But I'm like, these people are. He's driving a Lamborghini, and he's so stupid that he wanted to fill up his shower stall with Fruit Loops, and he had to take like 3 trips to the friggin' store because he didn't know how many Fruit Loops it'd take. I was like, well, who would waste so much time? Why wouldn't you calculate it first? But not people aren't normally physicists, so they don't normally do that. But that's another good question. How many Fruit Loops fit in a shower? Okay. All right. So let's continue on. Estimate the height of a building by triangulation and with the help of a sign, pole, and a friend. Okay. So what I've done here in this case is I've actually given you the drawing that the book gave you. Okay. What we have here is a person. Let me get a indicator up here. We have a person that's supposed to represent you. We have a sign pole right there. And what we're imagining the person doing is the person is looking up along this line across the top of the pole and getting in just the right position where by looking at the top of the pole, the top of the building is directly behind it, all in one straight line. Then, while standing in that position, looking in that way, he has a friend measure the height to his eyes, and that height is about 1.5 meters. And the height he is, or the distance he is away from the sign, which turns out about 2 meters. And then further, he goes ahead and measures the distance from the sign to the building. And the distance from the sign to the building is 16 meters. With this information, you should be able to figure out the height of the building. Let me show you how, because this hinges on some understanding of geometry, which again, a lot of people never got to take geometry. Just like me, I never got to take geometry. So I didn't know these things. Luckily, I did a brief stint after 9/11 teaching high school, and they had me teach geometry, which I never had. So you kind of quickly learn how to do geometry and how to master geometry when you're trying to teach it. So let me show you what I do. So it turns out that there's this idea of similar triangles, and similar triangles have equal ratios, meaning if you find two comparable sides of a triangle and then you find the same two comparable sides of a similar triangle, then their ratio of those two sides are the same. So what I'm talking about here is we have this triangle right here. And we also have this triangle right here. And more specifically, we have a third triangle that we could look at like this. Now, it turns out that smaller triangle inside, this one right here, that one's a similar triangle too, but it's not as helpful. Whereas this outer triangle, and I'll draw it this way, this outer triangle is way more helpful along with this other triangle right here. Notice this triangle and this triangle for that matter are all right triangles. The fact that you can make them inside of one another means that these two triangles are what we call similar triangles. So the height of this one to the width of this one is the same as the height of this one to the width of this one. That's a principle that you would learn if you had taken geometry. So that's the way I'm going to work it. From similar triangles, we have notice the height of that pole is 3 meters, but the height of the person's eyes is 1.5 meters. So this little height right here is only 1.5, and this height is 2.0. So that tells me uh, 1.5 meters, which is the height, divided by 2.0 meters, which is the width, is a ratio of height to width. Now, if I take the ratio of height to width for the bigger triangle, the height is this quantity, which I'm going to write right here. Hold on a second. This quantity I'll call H prime. Okay. That's not the, or excuse me, I need to go a little further down. There you go. This height is H prime. Okay. Now, that's not the height we want, and we need to keep that in mind, but it is the first step to finding the height we want. So I can now realize that other triangle is similar, and since it's similar, I can take the height of it, which is h prime, and divide it by its width, which is not 16 meters, but 18 meters. Everybody follow what I did there? Anybody have any questions on that? Let's
Uh, w- where did you get the 18 from? I
uh,
thought that was going to be looking at that, I assumed that was going to be 12, not 18, unless that's a 16, not a 10, and I saw
Yeah,
that
that
wrong.
is a 16. That's yeah, good job. Sorry
Oh,
about
okay,
my
I thought that
handwriting
was a
there.
10.
Yeah, good job. That is a 16. Sorry about that. So yeah, that's where it came from. 16 plus 2 meters is 8 meters. Does that make sense now?
Uh,
S-
yes. Yes.
Okay. So now I know 1.5 divided by 2 is 0.75. And to solve for h prime, I just multiply 0.75 times 18. So 3/4 of 17 is what we're trying to find. Well, 3/4 of 18 is what we're trying to find. 3 times 18 is 54. And then when I divide that by 4, that doesn't go so nice, but I do remember that 4 goes into 60 15 times. So this should go into it 14 times, but that would be 56. So it's a little less than 14. Maybe it's, let's say, 13.9. So H is, I'm going to say, about 13.9, and I'm ultimately just going to round this to one sig fig anyway. So I'm going to say H prime is about 13.9 meters. Now I got to remember, hey, I wrote down capital H equals question mark. It's very tempting and very common for you guys to write down the answer is 13.9 meters, but the answer is not 13.9 meters. The answer is H, and H is gotten by adding to H prime a distance of 1.5 meters, because that's the height of the triangle that we used above the ground. So when I add those two, I get 14.4 basically. Excuse me, 15.4 meters, something like that. So I would basically call this height of this building about 16 meters, about 15 meters, something like that. One sig fig would be enough, uh, but I would probably want at least two sig figs in this case. Anybody have any questions on that one?
Wouldn't 3/4 times 18 just be 13.5?
Yeah, I was just estimating rather than using a calculator. So I said I knew it was smaller than 14, and I'm only going to use one or two sig figs, so I just called it 13.9. But yeah, if you
Okay.
wanted to use your calculator, yeah, you do 18. Uh, 18 times 0.75 gives me 13.5. Oh, 13.5 is what it gave me. That's even better. So 13.5 plus 1.5 would be 14.5, 15, would be 15 exactly. So that gives it to you. Does that answer that question for you, Colin? I think that was Colin.
Yes, thank you.
Okay. All right. So that's another estimating type problem. And really the point here is to do it really quickly. It not I mean, in everyday life, it's to do it quickly, but on a test or something like that, it's not that important that you're doing it quickly. It's just a matter of you're trying to do it as conveniently as possible. And ideally, it would be great if you didn't have to use a calculator either. But, by all means, if you have a calculator, use it because it can save you some trouble. I'm going to go on to the next example unless anybody has any questions. I am now looking at the chat, so when y'all chat something, I can at least see it. I thought I had that window open, but I didn't. So here's another example. Estimate the number of times the human heart beats during the life of a human. So this is a very typical type of question to ask. And I gave you a note here because that's a note I tell my students every semester. But one of the neat things is you can use unit conversions to convert a year to seconds. And what you'll find is that when you do that unit conversion, the number of seconds in a year is about pi times 10 to the seventh. It turns out to be like 3.15, blah, 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 not 3.14. But to two sig figs, it's pi times 10 to the seventh. So that's a really nice estimate. I'm going to make use of that in solving this. How am I going to solve it? Well, I'm going to realize that we're always told the human heart rate is roughly 60 beats per minute. But I know from my own life and wearing an Apple Watch or a Fitbit before that, that my heart rate was almost never 60. I have found out now that I've been able to get decent night's sleep. I have found out that my heart rate during sleep will drop often in the low 50s, which is kind of nice. So that's a little helpful. But the main thing is, I notice the vast majority of the time when I look at my heart rate, it's at least 70, 72, 75, 75, something like that. Your book went so far as to try to call it 80. I don't know that I agree with that, so I'm going to stick with 70. Okay, so I'm going to say heart rate is approximately 70 beats per minute. Okay, I know that 1 minute has 60 seconds in it, so I can convert it to seconds. And I know that, at least in America, the life expectancy of humans is around 75 years now. So I'll say life is on the order of 75 years. So if I can figure out the number of times the heart beats in a year, then I just multiply it by 75, and that'll give me a rough estimate of the total number of heartbeats you can expect the human heart to go through in a lifetime. So that's what I'm going to do. I'll take 70 beats per minute times 1 minute equals 60 seconds. Now, 70 divided by 6 is the same, or 70 divided by 60 is the same thing as 7 divided by 6, which is about 1.166666 or 1.155555, something like that. Let me check real quick. 70 divided by 60 is 1.166, yes. Something like that. And that turns out to be beats per second. So now I can say 1.167 beats per second times pi times 10 to the second, or seventh, excuse me, seconds per year. Notice how the units work out with this. The seconds actually cancels out with the seconds, and it leaves me beats per year, which is nice. So I'm going to say this number times 3.14 times 10 to the, I got to remember where my times 10 to the thing is here, 10 to the seventh. And that gives me about 3.66 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the seventh beats per year. So 3.66 times 10 to the seventh beats per year times 75 years gives me roughly 2.75 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the ninth beats. So I would say about 3 billion beats is what you can expect the human heart to do in an average lifetime. Any questions on that one?
So this is just an overall question. So while we're
Yes.
doing these estimates, if I'm just to make sure that this is right, when we're doing these estimates, are we, is it not advised for us to use a calculator?
Oh no, you
Should we be?
definitely use the calculator all you want. I'm just trying to speed things up by not using it.
Okay, thank
And
you.
I'm staving off Alzheimer's, which is my big fear. I'm a hypochondriac, so I gotta do stuff to keep me from freaking out. So yeah, it's perfectly okay to use calculator. I do think it's a great skill and something that's good for your brain to use your calculator minimally. But that being said, I want you guys when you're trying to get a grade, I want you to use your calculator if your calculator's good at making your grades better. If your calculator's worse at making your grades better, then I don't want you to use it. But it's okay. You can definitely use it. Anybody else have any questions?
Yeah, I had a quick question.
Uh,
Go for it,
sure.
Daniel, and then whoever else.
So would that mean that that answer and whatever I get in the calculator would both be correct since it's an estimation, or would I have to get the more correct answer?
So the way well, it'll be self-explanatory once you start taking the practice test. You will see, like, if this was a question, they would have 10 to the ninth is one answer, 10 to the 12th is an answer, 10 to the seventh is an answer, maybe 10 to the eighth might be an answer, but probably when you're starting to talk about 3 billion, they're probably not going to have 10 to the 10th as an answer. So it's that big of a difference between right and wrong. And it's multiple choice. So it'll make life a lot easier for you. Does that make sense?
Yes, it does.
And far as the answer goes, what the right answer is whatever you round to when you round to one sig fig and you try to express it like 10 to some power. That's sometimes even better. So it depends on what you're wanting. Like if you're actually wanting to estimate a job or get some kind of price estimate or something like that, then the little number out in the front really might matter a bit. But if you're just trying to quickly get a power of 10 estimate, then yeah, throw that mantissa away from the scientific notation. Now, someone else tried to ask a question too at the same time, but I think Daniel got there first, or I might have misheard and let the wrong person go first. So, what's that other question?
Um, I was just wanted to make sure you said that for the test there's going to be a paper with like some of the formula for them.
Yes.
Just like okay,
Yeah, if you
just
look in helpful documents and links, there's something that says like PHY 242 allowed equations or chapters, 16 through such, or in your case, it's 241. So it'll say like chapters 1 through 11, 14, and 15. That's the equation sheet that you're allowed.
okay. I was just wondering because I was trying to think of like for the lake question, like trying to remember the cylinder equation off the top of my head.
Gotcha. The good news is if you look at that helpful documents and links, in addition to the equation sheet, it has front cover, back cover, page two, that kind of thing. Those are on the test as well when you take it, and you'll see that it actually has a lot of geometric formulas like the volume of a sphere and stuff like that. So, yeah, I expect you to know them, but I also give them to you.
All right. Okay. Thank you.
Okay. You're welcome. All right, let's do this next one. estimate the radius of the Earth. Now, that one's really pretty awesome, and there's a lot of different ways you can do it. For instance, if you happen to know roughly the longitude of Cape Hatteras and the longitude of, let's say, San Francisco, then you can quickly estimate the radius of the Earth because you happen to know that the width of the United States is about 3,000 miles, and you know that the difference in the longitudes is the number of degrees along the Earth's surface that the Earth goes through. So you can say, uh, 3,000 miles is to 70 degrees as R or as diameter is to 360 degrees, and then boom, you can get a rough estimate. That's another way. This one's kind of nice because I'm using the idea that the book had. If you have noticed, if you ever go to a really big pond, or if you just stand on the ocean front and watch a ship going out to sea, what you'll realize is the bottom of the ship disappears first. If you happen to be looking across a really big lake or pond, what you'll notice is if you see anybody on the other side, you only see them from like the knees up, or maybe you might only see them from the bottom of their bathing suits up, something weird like that. That's because it's almost as if the water in between you and them has bulged up in your way. And that's sort of right. Okay. So let me draw a really not to scale drawing real quick to make sense of this. And I will give you numbers and stuff like that. So here's a part of the Earth's surface. Here is a line, a radial line on the Earth's surface that goes to the center of the Earth. Now, actually, I went a little far. That's not very accurate as the center of the Earth. I'll say roughly like that. That looks a little better. And now this is supposed to be another radial line that I'm getting ready to draw now. So this line right here is also radial. And what I'm imagining is this is the body of the lake that you're looking at. Okay. Now, what you can do is you can go to a large lake, and I'm talking a lake on the order of 3 or 4 miles across. That would be your best bet. So it could be a lake, or it might be, for instance, the Currituck Sound or the Albemarle Sound or something like that. But what you can do is right at the edge of the water, you can put up a ladder, and then you can climb up that ladder until you can just see where the water is touching the shore on the far side. Because when you do that, you know that you're looking parallel to the Earth's surface at the other side. So this right here is a right angle. Now, in doing so, you had a ladder and you were standing up on top of it like this. Well, I should make that a lot bigger, obviously, because I'm not quite tall enough. So, and this is where, like I said, the scale is way the poop off. But anyways, I'm going to say, here's my ladder, here's my person, so on and so forth. And I'm going to say this eye goes right to there. And then what we have is a right triangle right here. And this part is another part of the triangle. Now, this distance from here to here is the radius of the Earth, and this distance is also the radius of the Earth. But again, by drawing it this out of scale, I make something not look quite so reasonable. What this distance is across the pond or across the lake, that distance is about 6.1 kilometers. Now, you can't see it because this is out of scale, but this distance is about the same as this distance because in reality, this triangle is really teeny. In reality, we're looking more along the lines of something like this. And this is still way too big. Okay. So that's more reasonable, but again, way too big still. So you can sort of see that this distance and this distance should sort of be the same. So with that in mind, we have a right triangle made of this red line, of this line and this line. And what we know is the Pythagorean theorem, a squared plus b squared is equal to c squared. Now, in order to pull this off, we need the height that your eyes are. And in this case, your height is 3.0 meters. That includes the height of the ladder plus whatever distance it had to go to get to your eyes, which really wouldn't be that far different from the height of the top of your head. So you could measure either one. But now with that, I'm going to say a squared plus b squared is equal to c squared. That's our Pythagorean theorem. In this case, what that means is the hypotenuse is the r plus 3.0 meters, which I'm going to call h, lowercase h, say. Okay. So what I have here is r squared plus 6.1 kilometers squared is equal to r plus h squared. Now, the h is 3 meters. I'm going to put that in, but I just wanted you to understand symbolically what I'm doing. So if we take and square 6.1, we get 37.21. So I'm going to get r squared plus 37.21 kilometers squared is equal to, now we got to square a binomial, so that's r squared plus 2rh plus h squared. Now you can see that the r squared cancels out from both sides because I could just subtract r squared from both sides. Now I'm going to put in my actual numbers, 37.21 kilometers squared, and that's just the kilometers that squared. We already squared the number, is equal to 2 times r times 3.0. Now, I've got one of these measurements in kilometers, so I can't have the r in, or excuse me, the h in meters. So I don't want to put 3. I want to take 3 meters and convert it to kilometers. That'd be 0.0030 kilometers plus 0.0030 kilometers squared. Now, you can tell when I subtract the 0.003 squared, that's going to be a very small number. In fact, it's 0.000009. So that's not going to matter at all when I subtract it from 37.21. So carrying on, I get 37.21 kilometers squared is approximately equal to r times 0.0060 kilometers. So r is 37.21 divided by 0.006, and that gives me 6,202 kilometers for the radius of the Earth. Now, it turns out the radius of the Earth, and this is the symbol we use for the Earth, by the way, is a circle with a plus in it, is 6.38 times 10 to the third kilometers. So I got 6,200 instead of 6,380. That's a really, really good result. So, by the way, anybody that wishes to conduct such an experiment, in other words, you can go to a lake or a sound somewhere that's on the order of 2 or 3 miles or more wide. If you want to drive there and do this experiment and try to estimate the height of, or excuse me, the radius of the Earth, I'll give you 2 points on your first face-to-face test as extra credit. So by all means, go out and do that if you want. Anybody have any questions on this one?
How would you want us to document that we actually did that?
You can take a couple pictures and you're just going to turn in the calculations and all the numbers you get. You can use Google Earth to actually measure the distance at the place that you're actually doing the measurements at and stuff like that. Just take some snapshots of the Google Earth photo that you took, the measurement that you took, and then show me your calculations and turn it in. It might involve some driving and stuff like that, but I think it's a worthwhile thing to do, and I'm certainly going to do it the next time I get a chance. I just haven't done it yet. Anybody else have any questions? I'm going to try to remember to write this up and put it in the week one module as a turn-in. Just keep an eye out for it there. If you see that I don't do it, send me a text message to remind me, and I'll do it as soon as I can. No questions on this? All right. Now we're going to move on to the next section, which is unit/dimensional analysis. So there's some facts that you need to understand. For instance, when you write an equation, then the two sides of the equation means that the left-hand side is equal to the right-hand side. That means the number part of the left-hand side has to match the number part of the right-hand side, but it also means that the unit part of the left-hand side has to equal the unit part of the right-hand side. And that's also true with this quantity we're calling dimension. Okay. Dimension is like the generic term because, in some sense, we might meet an alien species. And if we met an alien species, there's almost zero chance that there is essentially zero chance that they're going to refer to the same fundamental units of mass as a kilogram. So they're not likely to even have the same unit of mass as a kilogram, much less happen to have the same name. So instead of talking about units of kilograms, we can talk about dimensions of capital M for mass. Instead of units like meters for length, we can have a dimension of capital L for length. And instead of units like seconds for time, we can have a capital T. That's the difference. Okay. So units have to be equal on opposite sides of the equation, but also dimensions have to be equal on opposite sides of the equation, and the numbers have to be equal. Not only that, you've probably heard you can't compare apples and oranges. In the most fundamental mathematical way, what that really means is you can't add and subtract apples and oranges. Specifically, if you add or subtract one number to another or one number from another, those two numbers have to have the same unit or, as a bare minimum, the same dimension. Okay. And if you're actually doing the subtraction, you're going to have to actually convert it to some units and use that. But the main thing is they have to be the same. So adding and subtracting, the things have to have the same dimension and the same unit. Multiplying and dividing doesn't have such rules. They just act like X's and Y's when you multiply or divide units. But knowing all that, you can now say we might be able to use the fact that dimensions have to equal dimensions in expressions to come up with ideas of equations. So, in addition to telling you about the variable m that's used for mass and the variable x or y that's often used for length and the variable lowercase t that's often used for time, which has the dimensions of m, l, and t respectively in units of kilograms, meters, and second respectively, I'm going to also tell you that there are other quantities that can be derived in terms of those fundamental units or fundamental dimensions, like velocity. We haven't learned that yet. I expect you to know those top three. That's why I write you should know this now, right? But these other ones are ones that until we learn that material, I have to give you the units or dimensions of it. So for instance, V is something we use to represent velocity, and it has dimensions of L over T or units of meters per second. Acceleration has L over T squared, which is meters per second per second. Force, we often use as a capital F. And one of the few equations that people know from physics, even though they haven't had physics, is F equals, anybody can finish out that sentence? I'm talking about an equation. There you go. Ian did it. Oh, and I liked your answer about the $1 per beat and your 1% of Jeff Bezos. I like that, Ian. Yes, F equals MA. That's why I left it blank like that, because I wanted you to understand how we go about getting this. So F is equal to M times A should give you, just looking at M above, that's kilograms, and looking at A above, that's meters per second squared. So you get kilogram meters per second squared for the units, which is ml over t squared. There's another equation people know, and that's E equals
MC
anybody?
squared.
MC squared, right? So M times C squared. Well, if you square C, which is another type of velocity, you can see that would be L squared over T squared, and that's why we got the units of energy are kilogram meter squared per second squared, and the dimensions are M L squared over T squared. So now let's look at an example. If you believe that,
Um,
go ahead.
wouldn't we also get the same thing by just doing force by length? Just
Yes.
looking at it.
Yeah, that's another way, and you'll find out when we get to chapter, I think it's 7. It might be 6. Yeah, 6. When we get to chapter 6, you'll find out that work is equivalent to energy, and work is the integral of F dot dl, or F times x. So that's why that's the case. So good job. Yeah, so that was a good understanding of yours and a good notice. Now it says, if you believe the energy of an object depends on its mass and the speed of light, c, derive an expression that works based on dimensions or units. So let me show you how to do this dimensional analysis. I'm going to say solution E is equal to, I'm expecting it to depend only on M and C. And the most general way I could do this, and you've got to just sort of accept this and figure out that does make sense in your own time, but it's by multiplying M and C to different powers. So I'm going to take M and I'm going to raise it to the P power, and I'm going to take C and I'm going to raise it to the Q power. Okay. That's the most general way I can make an expression that involves M and C and have it equal to E. So now I'm going to attack this from a dimension standpoint. And I usually work with dimensions, but you can see you could do it with units. So working that with dimensions, I'm going to say E dimension has to be the dimension of mass raised to the P power times the dimension of the speed of light raised to the Q power. Now I know from above that the energy has has dimensions of m L squared over T squared. And I know that M has units of just plain M, has dimensions of just plain M, but I have to raise it to the P power, so it'd be M to the P. And I know C has dimensions of L over T, and I got to raise that to the Q power. So I can rewrite this as M to the 1 power, L to the 2 power. I think those are pretty obvious. This one might throw you a bit of a curve, though. This is T to the negative 2 power. Does everybody understand that that's the same as the right-hand side that I wrote before? ML squared over T squared? Okay. So that no one seems to be answering any questions, asking any questions. So that seems to be pretty good. Now, if we look at the right hand side, I've got M to the P, and I've got L to the Q, and I've got T to the negative Q. So just comparing them, I see 1 is equal to P, and I'm not sure that's right yet because I have to make sure all of the parts work or nothing's good. So I think 1 is P. Now I'm going to look at the exponent on L. L has an exponent of 2, and on the right-hand side it has an exponent of Q, so I'm going to say 2 is equal to Q. Again, until I complete this, I don't know if that's completely right. But now I can look at T on the left-hand side. That's raised to the negative 2 power. But T on the right-hand side is raised to the negative Q power. So these two are consistent with 2 is equal to Q. And now I see that that all works. And in fact, the answer is E equals M c squared, which is the famous equation. Now, this doesn't tell you there could be a unitless number in front of it, like 1/2 or pi or something like that, but it gives you a shot in the dark at least, and then you can just do experiments to figure out if it matches reality or figure out what pure number might be in front of it. So that's one example. Let me show you another real quick because we only got about 4 minutes left. Uh, the units of V, or the dimensions of V, are L over T. And since V subscripted normally means it's the exact same thing as V, we just subscripted it to mean it's at a different time or something. That's also going to be L over T. So I can agree that the V is equal to V0. That term is just fine. The other term, now I got to figure out though. The other term is 1/2 AT squared, and that gives you the dimensions of 1/2, the dimensions of A, and the dimensions of time squared. If that's not the same as the dimensions of velocity, then this equation is not valid. So the dimensions of 1/2, that's a pure number, so it's nothing. But the dimensions of A are L over T squared, and the dimension of T squared is T squared. So when you multiply those two, you just get L to the 1, T to the 0. But the dimensions of V are L to the 1, T to the -1. So this equation is not correct. So that's how you figure that out. One more example. Your book actually does this one, but I'm going to explain to you really quickly. What you're going to do with this one is you're going to say the dimensions of the Planck length or the Planck wavelength is got to be equal to the dimensions of the equation for Planck's wavelength, which I'm going to say is g to the p, h to the q, and then I'm going to say is g to the l. Now, I've already worked out what those units are, and if you go through this process, you're going to say this is L to the 1 power. We have an M in there, so I'm going to have to write M to the 0 power. We also have a T in there, so I'm going to have to write T to the 0 power as well for the left-hand side. For the right-hand side, however, the G is L cubed over MT squared raised to the P power. The H is ML squared over T, that's raised to the Q power. And the C is L over T, and that's raised to the L power. So I'm going to say I've got L to the 3P plus 2Q plus L. I've got M raised to the Q power minus the P power, like that. And then I've got T raised to the negative 2P, negative Q, negative L. So now I know that 3P plus 2Q plus L has got to be 1. I know that Q minus P is equal to 0. And I know that, I know that minus 2P minus Q minus L has got to equal 0. That turns out to be that's the ultimate result. So you guys are done. You can, of course, I want you to work this out on your own. We just ran out of time, but we have now finished chapter 1. If you've already chatted me your first and last name, you're free to go. If not, do that, and then you're free to go. But I'm also going to wait here till the last person leaves in case anybody has any questions. Thanks, everyone, for coming. Don't forget to let me know if you don't want your name on the internet, you don't want your anything on the internet. Make sure you let me know that by email. And everybody have a good day.
You too.
Thank you, Noah.
Hey, good evening. I have a quick question.
Go for it, Josh.
Do you know if this textbook, how long this textbook's going to be used?
It should be used for a while because he just came out with a fifth edition like last year,
Okay.
and it normally runs at least 3 to 4 years. It's been a while on his, and he's approaching retirement, so I don't think they're going to make another edition.
All right. Easy day. Thank you.
All right, have a good one, Josh.
Yep.
Anybody else? Giancoli, by the way, is he's an excellent author. This is an excellent textbook. I've been working for them since their second edition. I wrote part of the solutions manual. I wrote a website for it in their second edition. Then I wrote this website for it in their third edition, and even got mentioned in the credits and all sorts of good stuff. It's just a really, really good book. But they're all pretty good. Halliday Resnick's a good one. Actually, I love Ohanian. Ohanian's a really good one, but they haven't come out with their fourth edition, and I don't think they are going to. I think Ohanian either retired or ran into some health issues. Other instructors are other authors are Wolfson. That's Wolfson and Pasikoff. That's another good one. Surway, he was retired from JMU. He's another good author that writes the same level textbook, as well as the algebra-based physics. Does Ryan, Josh, or Joshua have any questions for me?
No, I'm good. Thank you.
No problem. All right. Well, I'm going to go ahead and call it a day. In case anybody, you're welcome, Josh. So I'm going to stop sharing. Thanks again for coming, everybody. I hope you learned a lot and hope I didn't blow you away with going too fast. But by all means, remember in the future, just stop me if I'm going too fast. And I hope you all have a good weekend. Make sure you knock out your homework by Sunday at 11:59 p.m. And thank you.